Hi everyone, welcome to today's class. And if we talk about yesterday, we tried to understand the very basics of GIS, right? So if there was someone not there in yesterday's class, I would highly suggest them to watch the first recording because without that to proceed, it will be a little difficult. Okay. So if anyone has any doubts from yesterday's session or they do not understand something, you can just let me know. Otherwise, we'll just do a quick recap and we will go to the topics that we have to study today. So yesterday we discussed about, we gave an example, we tried to understand the example of cholera epidemic. Okay. Then we talked about the very definition of remote sensing and what is GIS. Okay. So I told you that remote sensing and GIS, they go hand in hand. Okay. So one is kind of useless without the other. One, not even useless, you can say, if there is not, if we have just remote sensing and we can't do analysis because analysis part is done only using GIS only, then why are we doing remote sensing, right? And if we don't have remote sensing, we can't do the analysis. So they go hand in hand, and the existence of one is inevitable to the other. Okay. Then we discussed how the light from the sun comes to the objects on the earth and how it reflects, right? Every object on the earth has a different reflectance measure. For example, 100 units are coming and water may just reflect back only 20 units, and maybe the pavement is reflecting 70% of the units back. So that gets recorded in the sensor, and the sensor creates a image. Okay. Then we discussed about what is passive remote sensing, what is active remote sensing. Then we saw Then we saw different kinds of components of remote sensing, right? It can be a drone, it can be an aeroplane, it can be a hot air balloon, it can be small satellites, or it can be two larger satellites and International Space Station. Then we discussed what are the principles of remote sensing. Then we had discussed what is electromagnetic spectrum, right? So, how in physics what is an electromagnetic spectrum and how remote sensing is related to it, how do the products in remote sensing are created using these electromagnetic spectrum. So at different wavelengths, we discussed the character of atmosphere. So for example, oxygen in the atmosphere, it absorbs most of the gases, sorry, the oxygen in the atmosphere, it absorbs most of the wavelength in this bandwidth. Okay. So similarly, different gases absorb the different wavelengths. Then we discussed the definition of GIS. We talked about the spatial data, and we talked about what is attribute data. Then we did the very basic definition of what is a vector and what is a raster. So we will try to understand them maybe in this lecture or the next one. We will try to understand that in software, how we can visualize a raster or vector. Then we talked about the definition of pixel. So pixel is the smallest unit of an image. Okay. What happens is when there is a satellite, it takes an image of the earth. But what is the constituent of that image? So that image is divided into very small pixels. That pixels are very similar to the ones that you see in your TV. That is like, for example, in just an example in YouTube, you have like 720p, 180p, right? So that is the pixel value, number of pixel value. So similarly, here you have the number of pixels and in an image, and there is a digital number. So what this digital number is, this is the actual number of units that is reflected from here and recorded in the sensor. Thus, the sensor records that the amount of energy that is reaching its sensor, right? So for that pixel, it records the amount of energy in the form of a number, right? And that is stored as a image. So this is the basic constituent of a raster. Then we talked about the coordinate system. Uh, if you are new to today's class, I would I mean, if you didn't attend yesterday's class, I would say that please, you need to give good time to understand what is coordinate systems. You need to have a very good understanding of what a geographic coordinate system is, what is a projected coordinate system. So I explained to you in a geographic coordinate system that there is a geoid and we give a reference model based on which we create a reference datum. So datum from for different coordinate systems will be for different, if for two different geographic coordinate systems, the datum will be different because we are using different reference model. Then the datum can be either local datum and geocentric datum. This is the placement that we discussed and how it varies. Now we talked about projected coordinate system. So in projected coordinate system, we understood that there are three types of it. One is planar, one is cylindrical, one is conical. It is basically the projection of the shadow on the map and it is projected on the map. That part of the earth is projected on the map. So similarly here, in cylindrical one, uh, there is a special case that is UTM, which we are using 99% of the times, right? I explained how it is formed, how a UTM is formed. Okay. So the biggest overview to understand directly is once someone gives you a data and you click on it, if you get the coordinates value as degrees, then you should understand it directly that it is in a geographic coordinate system. Whereas when once you click on the point and the values comes out to be in meters, you can directly understand that it is in projected coordinate system, right? Then the next part today that we have to talk about is the concept of resolution. Now there is four types of resolution. What happens is uh, when you watch YouTube, right? There is 720p, 180p, 360p. As you select the smallest resolution, the quality goes bad, right? The quality goes bad. What is happening is uh, if you actually look, yeah. So what is happening is, for example, you have opened YouTube, right? This is your full screen YouTube, and you say 360 pixels. That means is 640 into 360 grids. So there is grids like this. These are pixels in the image. So there are 360 into 640 number of boxes in this image. Okay. So the more the number of boxes, if you increase the number of boxes, right, more the number of boxes, that is, the size of the boxes will get smaller, right? Because in the same area, you are adjusting more boxes. Okay. For the same image, you are adjusting more boxes. The size of the boxes will get small. Now, when the size of the box is bigger, you don't have a good output, right? For example, in 360p, the size of the box was bigger. So the image was not so clear. Similarly, when the size of the box was very small, when it was very small, it is more clear. Okay. So just taking in mind this concept, this is very similar to there are four types of resolution. One resolution is called as spatial resolution. Another resolution is called as spectral resolution, temporal resolution, and radiometric resolution. So the resolution is of four types. In general, whenever someone says just the word resolution, they are mostly talking about spatial resolution. So what is a spatial resolution? So I told you that an image, for example, the satellite took this image. At the at a zoom level of it, there is a small unit that is a grid, that is the pixel. Okay. So when there are more number of pixels in the image is more clear. Okay. More number of pixels means small size. Okay. Less number of pixels mean big size of the pixel box. Okay. So here you can see in this image, in this area, you can see there are three images. Okay. One image is termed as high resolution. Then it is next one is called as medium resolution, and third one is called as low resolution. So the number of boxes in this image is high. That is why it is called as higher resolution. What it means is the boxes is similar is by boxes I mean pixel, right? So the number of pixels in this image is high. So higher the number of pixels, lower the size of the box. Okay. So just remember this higher word means more number of pixels. Then comes medium spatial resolution. Then comes low spatial resolution. So low means less number of pixels, right? Less number of pixels means bigger box. So when it is less number of pixels, the image is blur. It is not clear. Now, what spatial resolution mathematically means is, so this box size, this pixel size, there is a length and breadth of it. It is always the same. Like if it is 10, if it is 10 centimeter, this will also be 10 centimeter only. So it is in the form of a square. Now, the size of this, for example, it is 10 by 10, 10, uh, 10 meters into 10 meters. Okay. So if the boxes in this image are of the size 10 by 10 meter, the pixel size is 10 by 10 meter, then I will say the spatial resolution of this image is 10. Okay. So if I say, because the box size here is small, right? It may be 3 by 3 meter, 3 meter by 3 meter. So I will say the spatial resolution of this image is 3 meters. Okay. So we just take the single side and we can call it the resolution. Okay. Now you must be understanding this part. Low resolution image has bigger size of box, that is 10. The word is low, but the resolution value is bigger, larger. Okay. So if I have a very maybe I have 0.5 meters into 0.5 meter resolution. Okay. So that means it is a very high resolution image. I will call it a very high resolution image. So you must have understood the relation by now between the size of the pixel to the terminology of high and low resolution, right? I hope it is clear to everyone. Anyone has a doubt? Okay.
No.
So, okay. So, if you see these two images here, this is a 0.5 meter resolution image and this is a 10 meter resolution image. This is a high resolution image. This is a low resolution image. This is very clear. Okay. Now, there is this one important thing that you need to understand here. For example, if there is an object on the ground that is of the size 3 meters, okay, 3 meter. So maybe it is a round object. It is on the ground and its size is 3 meter by diameter. Okay. Now, because the resolution is 10 meter and the object is 3 meters, you should be clearly able to understand that any object which is of the size smaller to the resolution of the image will not be visible in that image. Okay. So, for example, let us maybe call that this thing was 3 meters in size. Okay. But since the resolution now is of 0.5 meters, so it is very clearly visible in this image. Whereas here you cannot differentiate it. Okay. Now, for example, if there is a object of 0.3 meters here or maybe 0.2 meters here, it will not be visible in this resolution. You even need a higher resolution. Okay. So this is very important to understand this inference that what resolution actually means on ground. Okay. That if you are working maybe with a 5 meter imagery, okay, that means any object that will be smaller than 5 meter, it is not visible in that image. Got it? Now the next thing is we are clear with the part spatial resolution. Now there is something called as spectral resolution. Now what do we mean by spectral resolution? Now if you see, I have we have placed sensors in the satellite. We have created sensor. Now that sensor is only able to capture some of the wavelengths. For example, your day-to-day camera, mobile phone, it is just working in the visible range. Okay. So if you click a photo in your phone, you will see only these colors. Okay. So the sensor in your camera is just working in this bandwidth. Now, you must have sometimes seen there are night vision cameras. How are they able to see in the night? Now, they have the sensor which is working in this bandwidth, infrared bandwidth. So we have a sensor which can sense the infrared wavelength, and it is able to work even in night because there is infrared in the atmosphere. Okay. So similarly, we can create sensors that can capture other wavelengths also. Okay. In hospitals, we have X-ray. X-ray sensors captures the X-ray and gives you the output on the output of your fracture or anything, right? So we have sensors in all kind of bandwidths. Now the capability of my satellite. For example, this is my satellite, maybe. Sorry for my drawing because I'm just creating it with a mouse. Okay, this is my satellite. Now the sensor that is here, the capability of that sensor to sense different wavelengths, that is called as spectral resolution. Now, what it means is maybe I have a sensor that just works in two wavelengths, this wavelength and maybe this wavelength. So, the spectral resolution is that it can work in this wavelength and this wavelength. Okay. Maybe you have very complex sensor, very expensive sensor, and it can work across maybe five different wavelengths or maybe five different zones. So that is called as the spectral resolution. Now, to understand a very simple example of spectral resolution is when we talk about satellite imagery. Okay. When we are talking about satellite imagery is can be freely available to us from some sources, and from some sources it is paid, that you have to pay and it is available to us. Two such satellites that from which we can freely download the data, that is the imagery, that is one is called as Landsat and the other is called as Sentinel. Now Landsat 8 and 9, these are two different satellites. They are operating in the atmosphere, in the outer space. So we have these satellites that is called as Landsat. It is from the USGS Geological Survey of America. It is by the Geological Survey of America. Okay. So these satellites, they can work across these different wavelengths. So it can work across these different, the sensor is able to detect these wavelengths. So for example, it can take a image in this wavelength, it can take a image in this wavelength. Similarly, in all of them it can take a image, and it has named all of them. So if you see, there are two things mentioned here. One is this resolution. So this is the resolution that is the spatial resolution, that is the size of this box. So the spatial resolution of Landsat satellite is 30 meters, and in this one particular band it is 15 meters. Okay. Then there is another satellite by European Space Agency, that is Sentinel-2. Also recently Sentinel-3 has been also launched. So it has a spatial resolution. For some bands it has as big as 60, but for some bands it is as low as 10 meters also. So because it is freely available, Sentinel-2 is much more beneficial to use than Landsat 8 because the resolution here is overall 30 meters, whereas the resolution here is in some bands 10 meters. Now, your satellite was able to take the images in 11 different bands. Okay. So these bands are because of these wavelengths that in this band it took a image. That is why it is called a band, right? Now the word spectral resolution means the capability or the ability of your sensor to take different band images. So I would say the spectral resolution is here is this these bands. For example, if I have maybe any if I launched a new satellite, okay, and that is able to just take the images in this four bands only, then I can say the spectral resolution of Landsat 8 is very much better than the spectral resolution of the new satellite, because the new satellite is just working in four bands, whereas the Landsat is working in 11 different bands. Okay. So the spectral resolution means the variability of the wavelength at which it can take image. Now, when you have a sensor which can take image from one, which can take images in 1 to 100 bandwidth. That is number of. So if you see, this is 11. What if it was maybe until band 66? There are 66 images in this. Okay. So 1 to 100. If it is from 1 to 100, it is called as a multispectral sensor. A sensor which can take the ima- uh, band images in across 1 to 100 different bandwidths. Okay. But what if I have a sensor? What if I have a very specialized sensor that can maybe in a certain range, maybe this is the range, and in this range, it can take at 1000 points, at 1000 different wavelengths, it can take the image. Just imagine 1000. So when the number increases from hundreds to thousands, it is called as hyperspectral sensor. Okay. So when it is a number below 100, it is called as multispectral. When it goes beyond 100, it is called as hyperspectral. So some examples of multispectral is one is Landsat, another is Sentinel. Okay. So maybe if I ask the Google examples of hyperspectral sensors. So the most famous one that I know is Hyperion. Okay. For example, if we check the number of bands in which Hyperion sensor works. So it can work in 242 wavelengths. So it means that it can take 242 continuous images at uh, different wavelengths. Okay. So I hope the difference between multispectral and hyperspectral is clear. Okay. So we are done with the part of spatial resolution and what is a spectral resolution. Is there any free hyperspectral image? Okay. Even I have not worked with hyperspectral, but I hope so. There is some. Are there free hyperspectral images. Okay. So the Hyperion itself is free. Hyperion can be downloaded from Earth Explorer. So uh, we have EHU hyperspectral. So yes, Maxar open data program. So it is very easily available. Okay, yes. Okay. Now we talked about spatial, we talked about spectral. Now then there is temporal resolution. What do we mean by the word temporal? So temporal, if you try to decode the word, it looks maybe something related to time, right? Temporal. So what happens is, this is your Earth, right? And your satellite is going around the Earth. Okay. So maybe your house is here. Okay. So that satellite is going. Now, what is the time? Maybe today it took a photo of this region of yours. The satellite was here and it took a photo of this or the image of this region. Okay. Now, when is the next time that after the rotation that this satellite will come again back here at the same place and it will take a image of this same place? So the time the satellite will take to come back to the same place is called as temporal resolution. Now, if we talk about Landsat and Sentinel-2, okay. So a Landsat 8 satellite will come to your place after 16 days, okay. Whereas a Sentinel will come after 5 days. So the temporal resolution of Sentinel-2 is low, okay. So what will happen is, for example, now, maybe there is a fire in the forest near my house. Okay, this is my house. This is a forest near my house, and there is a fire here. Okay. Now, the satellite came today, maybe on the first. Maybe just imagine today is 1st of December. Okay, and the fire was so intense that the fire was there from 1st to 6th of December. Now the satellite will again come here on the 5th of December. That is 5 days. Okay. Maybe it is 6th, but you can check, right, how 5 days matter. So maybe it is coming again. And on the 6th again, it is seeing that it took a image and we are able to analyze the fire, extent of the fire. But what if the Landsat image, this is the Sentinel, right? What if the Landsat satellite comes and it came on the 1st, then it is coming back on the 12th. So you are unable to make any proper observation. So it is said that more the temporal resolution is low. That means if the temporal resolution is maybe 1 day, 2 day, then you will be able to analyze your area more. Okay. So basically temporal resolution is how the satellite is visiting that area again, the time. So if you have a process, maybe that is spanning over 15 days. For example, not 15 days, maybe just say your neighbor's building is being constructed, because construction takes a time, right? So you can monitor that even in Landsat also, because after 10 days some construction will be completed. But in Sentinel you will be able to understand the construction after every 5 days. So whereas in Landsat 12 days, whereas in Sentinel in after every 5 days. Okay. Now then there is the third concept, that is called fourth concept, that is called as the radiometric resolution. So this is also related to the capability of the sensor. Now what in actual is radiometric resolution? So what happened was, if you are computer friendly, if you have some knowledge about computers, when you install something it says 64-bit, 16-bit, 32-bit, right? What is that? What is actually happening is, if you go to previous times, if you go to historic times, you must be remembering that there were black and white TVs. Slowly we were able to produce color TVs. So just like the same, because when the image is captured by the sensor, it by default, when the image is captured by the sensor, because it is calculating just the energy, so by default it is producing everything in grayscale. Every band image, every image is just produced in grayscale. You may have a red band, but it does not mean it is red in color. The pixel values are there, but by default it will appear only gray only. It is for you that you can change its color to red to visualize. So for example, I have downloaded one imagery. Do not worry about how imagery is downloaded or how it works. We will understand it in future classes. I'm just showing a reference. So if you see, this is a Sentinel image. Okay. So in Sentinel, there are different bands, right? Uh, in Sentinel, band 2 is at the bandwidth of blue color. Band 3 is green, right? So maybe I have band 2 here. Okay. So I open this band 2 in my software, GIS software. So now you see that everything is gray, because by default the sensor will take the images in gray only, because based on the digital number. It is for you to understand that it belongs to the green band, that this image belongs to the wavelength of green band. The sensor will give every image in gray only. So maybe if I take 4, right? This is also gray. Now there is this one something, there is the ability of the sensor to differentiate between the color of gray, the shades of gray. What it means is, as technology is developing, we have been able to define more shades in a single color. So when this all started, initially we had 2-bit, 4-bit, 8-bit, then it increased to 64-bit, and now we have more. So what this bit means is, so so what happens is, if you have a 4-bit image, that means 2 raised to power 4. 4-bit means 2 raised to power 4. So if you calculate this, it means 16 levels. That is, you were able to differentiate gray color into 16 different shades. So as technology is improving, we created sensor that was able to go ahead 6-bit, 8-bit, 11-bit, and now we have up to 16-bit of satellite. Then for computers we have developed even more, but I think for satellite we are currently at 16-bit, right? So 16-bit image means that a single gray color can be differentiated into 65,536 different values. Okay. So if you see Landsat 8 and Sentinel 2, they both belong to 12-bit, right? The multispectral sensor of the Landsat 8 and the Sentinel 2, that belongs to 12-bit. That means whenever I open an image, if you see the range value of this pixel numbers, that is the uh, digital number of each pixel. So because now we are able to differentiate gray 12-bit, that is 4096 times. So this is almost, the range is from, uh, if you subtract this from here, the range is of 4096. Okay, got it? So it is the ability of the sensor to differentiate the gray color. So uh, both the Landsat and Sentinel are 12-bit. I hope the concept of resolution is clear to everyone. Do you have any doubts in this? No. Okay. So just imagine this one thing. Our computer that we are working on is, my computer is 64-bit. Okay. So just imagine 2 raised to power 64. That is the amount of colors that my computer can differentiate in a single band. So that is very big achievement of us humans. Okay. So the next thing that comes is, you need to understand how these bands work. What is the application of these bands? So how do we actually use these bands? Now, what happens is, just consider, if you see here, the sensor took, for example, band 2. So the wavelength that belongs to green color, this whole image is just taken in that band. Okay. Similarly, it took at 13 different wavelengths. Now, what happens is, if you look at an image taken in a single band, so don't look at this right now. Don't, because this is something that you see with your eyes, you will be able to understand. Don't just ignore these two images. Just look at this image. So this was just taken in red band, just red band. And this image is also taken in red band. If you don't get to see this, can you tell me that this is water? Right? You can't tell me. Can you tell me this is vegetation if you don't have these true color images? If you don't have these two images, you will not be able to understand if this is what is it on the surface. Okay. So what I mean is I have this image of band 2. Can you tell me what it is? You can't, right? You can't do analysis with just a single band. It becomes very difficult. Because you know this is a city, because you have a knowledge that is why you know, but where you get stuck now, can you tell me what this is? You can't, right? So what happens is, as I told you, um, that every object on the earth has a certain character, what amount of energy it reflects, right? So maybe just take an example that there is the red band wavelength and the green band wavelength. Now, when it comes to the maybe let us just assume two wavelengths are coming, that is red band wavelength and green band wavelength. Okay, so when the red band wavelengths come to the grass, so maybe 100 units of energy was coming and it reflected only 30 of it. Uh, okay, and when green band wavelength energy was coming, it only reflected 10% of it, and rest was absorbed by it. Okay. So every object on the Earth's surface has its own unique characteristics, how it will interact with that particular wavelength, right? So there are, for example, if you are doing an observation with Landsat imagery, so in every imagery, the brightness value of grass will be different because it is reflecting different amount of energy. Maybe in one band it is very bright, in another band it is dark. So it is the unique property of the object on the earth, how it is doing the reflectance of that particular wavelength. Okay. Now when we are observing just in a single band, when we are observing just in a single band, what happens is, for example, we particularly talk about red band. Now when the sensor took the image in a red band, this vegetation, this all is vegetation here, right? The reflectance of vegetation, the reflectance, so from the sun, red band energy which came and got reflected, and the sensor captured that energy. So similarly it did for water also, but in red band the value that will be captured, because the reflectance is very similar of these two objects. So when you are working in a red band, you are unable to differentiate between vegetation and water. They both will look to you similar because the reflectance is very similar. Okay. So this is also a unique character, that somehow the reflectance of these both is similar, but some other objects is different. For example, this area here it has a different reflectance than this vegetation. Okay, so the barren area has a different reflectance value. It has a high reflectance value, whereas vegetation has low reflectance value. That is why it is appearing dark. Okay, now just like red band, there is a near infrared band. So a near infrared band is working somewhere in this bandwidth. Okay, so when you when the sensor takes an image of earth in near infrared, then there are some objects, for example a fallow land and a vegetation. They have similar number of digit reflectance value. Then you are unable to differentiate in this image, whereas you can clearly understand what it is here on the real image. Okay, so sometimes it is very difficult to differentiate two objects in a single band. Okay, so in that case what we do, this is another example, that is in near infrared band you are unable to differentiate between snow and cloud. So here they look very similar. Okay, then we create a curve about what? So the vegetation, the reflectance of vegetation in different bands. Okay, so for example if you took an image in uh, so band 1 in, okay, this is red band, this is blue band, this is green band. Okay, RGB, R, G and B. So the reflectance of vegetation, that is how vegetation looks. So the reflectance of vegetation is very low in visible range. So it absorbs and reflects less. Whereas the reflectance of vegetation in near infrared is very high. What it means is, now what it means is, when you look at this vegetation, the reflectance of it, if the energy is NIR, okay, the reflectance of it is very high. Maybe 100 units came and it is reflecting 80 units. So for vegetation, the reflectance is very high. What it means is, because our human eyes are just limited to see things in visible range, because our human eyes are just limited to see in this range. What if God made us capable to look in this range also, NIR? Then the vegetation would not appear to you green. It would have rather appeared to you in this color of NIR. Why? Because the reflection is more high in this. Whereas you are not able to view this color. That is why you are just, if you see in red, green, and blue, the reflection is highest in green. That is the green band here. So that is why you are seeing it in green color, because your eyes are just able to see in this zone. If you were able to see the NIR also, right, then you would have rather seen vegetation in the color of whatever. If we were able to see it, it would have appeared to us in near infrared, not green. Okay, this part is clear to everyone. This is like a concept, right? This needs, you need to have a clarity on this. Okay, so if it is not clear, you can tell me. So what happens is, just imagine uh, every object on Earth can be placed on this curve. So that object will have kind of a graph of its reflectance value, how it looks like. Okay. So if you talk about barren soil, okay, it has the highest reflection in infrared. It has the highest reflectance value in infrared. Okay. And if you talk about the character of water, so if you are working in visible range and a little bit of infrared, the water gives some reflectance. After this particular wavelength, the water has zero reflectance. That means it absorbs everything. So if there is a pond of water, this is a pond of water, and there is a wavelength coming that is beyond this zone. That is beyond this zone, not this zone, beyond this zone. So if that wavelength is coming, 100% of it will be absorbed by water. Nothing is being reflected. Okay. So everything has a unique character in universe. That object, how it behaves with the wavelength is dependent on the object, how it is unique. Okay. Now, why we have different bands? How do we use these different bands? So, for example, Landsat is taking 13 different band images. How can we utilize them? So, first we talk as we progress into remote sensing and GIS. There is something called as band ratio. You need to understand what is band ratio. So, to understand band ratio, let us consider, you need to mathematically understand this. So, for example, just for the case of vegetation, you had this curve, right? Now, I want to understand vegetation better. I want to understand vegetation on Earth better. So, I have its curve, how it looks like. To understand it better, I have to use this mathematical uh, way. That is, I will take the imagery in a wavelength where the reflectance is very high. So I will take one image in near infrared and I will take another imagery where the reflectance in the same, for the same object is very low. Okay. So in red band, if you see in red band, that is this one, the uh, reflectance is very low. Okay. So for example, if maybe I'm talking about soil, this was particular case of vegetation. Maybe if I'm talking about soil, I see that uh, the highest is in this area almost. So you can either take this or maybe this, one of them. Okay. One image from this area and another one I can take from this one. Okay. So I have to select two images. I can select as many as I want, but to understand this, let us take two images for now. And based on these two images, we create a index, that is a ratio. What we do is we put every pixel of near infrared and subtract it with the every pixel of red band. So we take two images, that is the band image in near infrared and we take the band image in red. So we create a mathematical equation. This equation is created in a way that the result of it is in a range -1 to 1. Okay. So what this -1 and 1 means? So because if you remember this, in this bands we selected based on the vegetation. So this -1 to 1 means 1 is the highest probability of it being vegetation, whereas -1 is the very lowest probability. So it is kind of a probability range. More we are going towards 1, we are sure that it is vegetation. Okay. Now, this mathematical band ratio, we also call it as index, or we also call it as indices. Okay. So for particular case of vegetation, we call it normalized difference vegetation index. Okay. Now, to understand the variation of it. So, I told you it varies from -1 to 1. To understand it better, if it ranges from -1 to 0, it means either it is a dead plant or it can be negative values correspond to anything else. Either it can be water surface, man-made surface, but it is for sure it is not a plant. Okay. Then 0 to 0.3, it means a unhealthy plant. Okay. Then 0.3 to 0.6 means moderately healthy plant. 0.6 to 1 will mean very healthy plant. So if the values are above 0.2 for a pixel, we we are sure that it is a plant. Okay. Is this part clear to everyone, NDVI? So if you come across any doubts, just don't keep them with you always. Why is red band taken for vegetation, not green? Okay. So if we go to this image again here, if you closely look, okay, so this is the green band, this is the blue band, and this is the red band. So it was hitting a low more in red than compared to green. Okay. So that is why we took red band. But because it is a substantial difference from near infrared here to here, you can also take green. There is no problem. You can also take green, but you are getting better results with red, then I would probably use red only. So if I have a satellite which is not giving me red band, okay, then I would rather of then my first choice would be to choose blue instead of red. So if my satellite does not even have blue band, then why not? Yes, I can choose green also. So then it will become NIR minus green by NIR plus green. Okay. So similar to NDVI, we have many other indices also. Like there are many indices because there are 13 bands, right? You can create many complex mathematical equations. You can create as many equations you want, right? So there are, you understood the part, right? So that you are trying to do some analysis using two different bands. Now instead of two, you come up with some mathematical equation that you may take three bands, four bands. It depends on you. So there are some ratios that are already defined. Okay. So for example, after NDVI, there is something called as soil adjusted vegetation index. There is land surface water index. The formula is this. So NIR is near infrared range. Okay. SWIR means short wave infrared. These are different wavelengths in infrared only. Okay. So for example, here we have different band ratios. Now, if you want to study more about band ratios, if you are working in research or something, right? So there is this source. You can just simply look for different type of remote sensing indices. Uh, yes, this website that I particularly use for my reference. This is index database. So, for example, there is the sensor selection option. You select which sensor you are working on. For example, we are working on Landsat, right? So I will choose Landsat, and it will give you different band combinations that you can do. So these are very different equations, and every equation has some meaning, something, some inference that you can find out. Just NDVI was very simple, right? So there are very different things. So you need to research upon it to understand them better. Okay. So this is the website. I'm sharing it in the chat box. You can look it for your reference. So if you're working with some other satellite, maybe if you have the option to, maybe there is Worldview. This is paid satellite, right? Its resolution was 0.5 meters. So if you have the access to it, maybe you will find some better indices. You can try these also. Okay. So let me give you an example how to practically uh, calculate indices. Okay. I will show you in the next, there is this part that I will show you how to download data. But before that, let me show you just a practical version of it. Okay. Don't worry from where I'm getting the data, or maybe if you are not familiar to QGIS, do not worry about it. Okay. I'm just giving an example right now. Okay. So we know that if I'm working with Sentinel imagery, and in Sentinel imagery, if I have to calculate the NDVI. So the formula of NDVI is near infrared minus red by near infrared plus red. So in Sentinel-2, near infrared is band 8 and red is band 4. Okay. So let me bring in band 8 and band 4 in my software. Do not worry about how I am doing it. I just want to show you the results. Okay. Now this is band 8 and band 4. I want to calculate NDVI from it to better understand my vegetation. Okay. So there is something called as raster calculator in every GIS software. Okay. So what you can do in raster calculator is you can always do some mathematical operations. So if you see here, this is mathematical operation, right? I have to minus it and then to divide it. So first what I will do is, because baud mass is important, right? Otherwise there is option of some errors. Now first I will write near infrared minus red. So that is band 8 minus band 4 divided by band 8 plus band 4. Got it? I have to save the layer to my computer. Maybe I'll call it NDVI demo, NDVI demo 2. Okay. And I press OK. So we got a new image. Now, if you see, the values here could have ranged from -1 to 1. It is between -1 and 1. Okay. uh, this is 0.21 here and 0.7. Okay. So what it means is the maximum range here is ranging to zero point 0.7 and the minimum to 0.2. Now I want to visualize this. I will go to properties and maybe change its color. Okay. So now the blue color is near to 0.7. So if you see here, I have a value at every pixel. If I'm, if just look at this one, just look here. So as I'm moving over every pixel, the value is changing, right? So as I'm going over to the blue one, the value is getting near to 1. Okay. It is 0.5, zero point 0.6. So it means it is for sure it is vegetation. And now I can simply understand. For example, I talk about maybe this point. Uh, okay, this particular pixel I selected. I selected this pixel and it has a value of 0.57. Now I can straightforward say 0.57 falls in this range. It is a moderately healthy plant. Also, it depends on season to season, right? Because in some seasons there is fall of leaves, the plants dry out, right? So maybe there is a season when the vegetation is at a boom. So you will find more plantation that is in the value of very healthy plant. So it depends also on the season and season. So maybe this red one, if I choose the pixel value here, you see it is minus 0.11. So if you remember from here, it should be at least zero point 0.2 to be a plant. So it is for sure that it is not a plant. So it is not a plant and it is in minus. I am very sure it is something else. So our aim to create this indices was just to understand the crops better, just to understand the vegetation better. So similarly, if I want to understand soil better, I will use the soil indexes. If I want to understand water better, I will use the water index. Okay. Now, there is this one important thing that you need to understand, that is how to download Sentinel-2 data and how to download Landsat 8 data. So, the very first important thing to download data from these two is you need to have a account on these websites. First is search on Google USGS Earth Explorer. Okay. So it will look something like this. Click on it. So it will open and it will have a page like this. And you need to create an account here if you don't have an account. If you are gonna work in GIS field, I think it is very important to have a USGS account. Okay. So first create an account here. Just let me know in the chat if some like if how many of you already have an account here. Just want to see something. Does anyone already have an account here? Good. Okay. So the people who do not have account, just create an account here. Okay. This is USGS. And okay, so the vast majority of people do have an account. Good. Is it possible to calculate this calculation for RGB sensor? Uh, yes, in raster calculator, when you go in raster calculator, okay. So for example, if here I have added my RGB here instead of this green and blue, I can just add RGB here and do any kind of calculation I want to do here. Okay. So it also depends that what you want to achieve from that calculation. Okay. Yes, this is the website. Yeah. So just create an account here. And the second thing is just go to this other website. Just write on Google Sentinel-2 download. Okay. This will open a Copernicus data space ecosystem. And in here, in this website, there is this option called as Explore Data. I think their website is down. So I'm just sharing the link here. Okay. You also need to create an account on this website. So this is also important because Sentinel data is much more better than Landsat data, right? So you need to also create an account on this website. This is not working for now. Let us leave it that way. So once you log in into your USGS Earth Explorer, okay, this also has opened. So you need to log in into this one also. Now, once you open your Earth Explorer, USGS Earth Explorer, how to locate your place or how to mark your data. Okay. If you come on the left side, you will find a search panel. What happens is there is something called here as written as US feature. So if you are working in US, just select US. Otherwise, for example, I'm looking for an image in India. I will rather select world feature. For example, I'm looking for the city Chandigarh. Okay. So I will just write Chandigarh and click on show. So just look out for your city's name or somewhere. Otherwise, there is option to just directly pan and zoom. If you know where your data is, just directly can go to your location, okay? Or if you don't know about the location, you can search it here. So for example, I searched about Chandigarh. So it has given me a place mark over Chandigarh. Now this place mark has been added to my coordinates. I don't want it for now. Let me close it. If you have already a shapefile, don't worry if you don't know what a shapefile is. If you know shapefile, you can directly upload your shapefile here and it will select your region of interest. Okay. So, for example, I want to work in this area. In this area, I will I will zoom into this area, zoom it into an extent where your area is properly visible, for example, and then select this thing that is called as use map. So once you select, it will create four coordinates at the, when you zoom out, it will create four coordinates at your selected area. Maybe you can change it to your particular area selection. So just move them as you want. Okay. Now the next thing is, just below this, there is an option about cloud cover. So what is cloud cover? When the satellite takes an image, if there is very big clouds, right? If there are very big clouds, then the image will be obstructed, right? The things will not be clear. So why would you want to use an image that is not clear? Rather, I would look for an image that is easily visible. So you can just select the percentage of cloud cover, that I don't want more than 20% clouds in my image, or maybe more than 30% clouds in my image. Okay. Then you have to select this data sets. Once you select the data sets, uh, maybe there is dates also. Sorry. So just on the left side of cloud cover, there is date range. So if you leave it empty, it will give you the latest date. Okay. It will give you the latest data first. Maybe if you want to do an analysis about a certain month, maybe I want to do analysis from for the 1st of January 2025 till July 31st, 2025. Okay. So you can select the date range also and then click on datasets. And then there are different products of satellites. So someone asked me about Hyperion also. It will be somewhere available here only, somewhere in this only. But if you just talk about Landsat, just click on Landsat. In this, you will find Landsat collection 2 level 2 data. I will explain in the next classes, upcoming classes, what is level 2, level 1. But just now remember that for our particular reference now, we are selecting level 2 data. So Landsat 4 and 5 and 7, these were previous satellites. So for example, you are working, you want data from the year 2000. You want to do some analysis with the data from 2000. It might be either available in this or in this one. Okay. So you have to look in which of the date range your data will be available. So the latest data is available in Landsat 8 and 9. So I will just simply select it and click on results. So if you see here, the images of this area given by the latest one, that is the last range of my data range that I've selected, it is appears here. Now there is this footprint option. So if you click this, it will tell you this is the image size, like the images like this. If you want a preview, You can just simply click here. It will take a little time to load. It gives you the actual preview of how the image is. So if you see in this image, there are some clouds. So if your area of interest is here, this will not be much a useful image for you because there are clouds in this region. Okay. No, it is not zero. For example, I just said I chose 20%, right? Now in this image there is 20% cloud, but I want to work in this area and there is no cloud in this area. So I can clip out my area from this. So the clouds here do not bother me. You have to look every time if the clouds are coming in your way. Okay. So 20 to 30% is always a good estimate to choose. Okay. Now, for example, let us have a view of this one. So in this, there is no cloud cover. It is a very clear image. Okay. So this will be rather useful for us. Now, there is this option here to download. When you click download, there is this product options. Click on product options. If you have to download all the bands, it is here. Okay. That everything in that image will be download, all the 13 bands. If you just want to download some particular bands, maybe you just want to calculate NDVI only, okay? Then you can download 5 and 4 directly, just these two bands. If you just want to evaluate the NDVI, why to download the rest of the data? It will not be useful to you, right? So just simply click this and it will start downloading. So for your reference, I would suggest just keep one sample downloaded and keep it in your computer for future references so that we can do the practicals. Okay. So we understood how to download data from Landsat, and tomorrow we will see how to download data from Sentinel. Just create a login for this also. I have shared the link already. Just create a login for this also. Okay. So in today's class, does anyone has any doubt, please? Okay, good. So, in case you watch the recording or you come up with any kind of doubt, you can always reach out to me. It is not a problem. Okay. Just drop me message on the WhatsApp or something. We can always discuss. So, uh, today's session is ended, but just remember, uh, before tomorrow, you need to create two logins. One is USGS login and the other one is the uh, Sentinel 2 login. Okay. Then, okay, then until tomorrow, have a good day. We'll see each other tomorrow then. Okay. Bye bye.